What is up, everybody? Welcome to lesson 2, which is going to be gel electrophoresis. Here is the assignment as you see it. So let's go through it. It says, please watch the video lesson that I made. That's this video. So if you're watching it, you're already doing number 1. So good on you. And number 2, it says, follow the link below for the virtual gel electrophoresis lab and complete all the work that is asked of you on the lab on a Google document. And upload it to this assignment. Okay, so I'm going to go through that with you now so you know exactly what you have to do. So I'm not posting questions underneath here or anything like that. All the questions are going to be in this lesson, right? So when you click this link, it'll bring you to this web page.
A local neighborhood has been the scene of several recent bicycle thefts. Explore the lab to learn what is available for your
Okay, thank you very much for that. Actually, that's not the website that you're going to. I mean, it's the website you're going to go to, but it's not what you're going to see. So let me show you what you're actually going to see when you click this link. Okay, so when you click that link, it's going to bring you to this little menu area. Okay, now it does require Flash. If you are having issues with that, I'm using a Chromebook. So all you have to do on Chromebook is allow Flash to be used on your browser. It's really not that hard. There's like a little lock that comes up here that says, or a little puzzle piece up here that says that Flash has been disabled. All you have to do is like right click on that and manage the settings. And it's very easy. If I can do it, you guys can definitely do it. But once you finally get it up and running, you want to come down here and click on the gel electrophoresis exercise. And it
a
will
local
load,
neighborhood.
It will load this up. Okay, so you're going to go through this whole thing. And it says problem, and it says explore.
Explore the lab to learn what.
Okay, and then it says the procedure. Okay, and you're going to follow all the directions for this. Okay, and then once you are done with all of that, okay,
Gel electrophoresis.
once you are done with all of that, you can then answer
A
some
local
questions.
neighborhood has been.
God, I wish you would.
Explore the lab to learn what is.
Okay, so you're going to click on each one of these things. I'm going to talk about them as well, but you're going to click on each one of these things here. Okay, and these are the questions that you have to do. So when you click the lab notebook, this is what's being graded. Okay, so you're going to click this lab notebook, and these are the things that you're going to answer. You're going to answer these on a document, though. You're not going to. You can answer them in here as well, but you need to add them to a document. Okay, so make a Google Doc. Okay, so when you bring this up on your area, over on this side, over here, it'll say create under the assignment. So you hit create and then add a Google Doc. And what you're going to do is you're going to, write this question, explain how comparing DNA fingerprints can help identify a person who has committed a crime. Write that on the Google Doc, then answer it on the Google Doc. Okay, then there's data here. Okay, I want you to create this chart on your Google document. All right, so copy and paste all this text, okay, in the table below, record the estimated length, blah, 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 and then make this on the Google document, okay? It's very easy to do, to make a chart. So it's, it's 11 columns down because you include the title here and then 10 rows of data. So that's 11 columns vertically. And then 1, 2, 3, 4, 5, 6 columns left to right. So it's 11 by 6. And then you fill in all the data. Okay. And you will get this data by going through the lab. All right. And then the last thing is these 5 questions. Okay. 6 questions. All right. So just to be clear, we're going to do the prediction question. We're going to create a data table that looks just like this on our document. And then we're going to answer that analyze and conclusion questions. We're going to do all of this on a Google Doc. Okay. So if anybody has any questions about that, make sure you let me know. But that's what we're going to be doing. Okay. So now that we understand that, we can go back to the actual lesson here. Okay. So what we're going to be doing today is called gel electrophoresis. Okay, try to make this quick. Electro means electricity. Okay, I'm not sure what phoresis means. I want to say that it means just movement. Okay, or the size. And gel means it's happening in something called a gel, just like Jello. Okay, just like the stuff that you would eat for dessert, the little gelatin stuff. Okay, and what this does, what gel electrophoresis does, it allows us to compare DNA by size and charge. Okay, so we learned about DNA in the, a couple of lessons ago, and we said that, DNA is this long ladder-like compound that has A's, T's, G's, and C's in the middle, and it has ribose sugars on the ends and all this good stuff, right? And it's your genetic material. Well, sometimes we want to compare DNA between organisms. Sometimes we want to compare bacterial DNA to other bacterial DNA to see what likenesses they have. Same thing for humans. Okay, so if I take an individual A and I take that individual's DNA and I take individual's A's father, and we'll call individual A's father, individual B, and we take a look at their DNAs, their DNA should be similar. But how do we actually study that, right? How do we say that A is 99% similar to B, right? That's one thing that gel electrophoresis can help us do. All right. So in the past lesson, we did something called DNA isolation. We've isolated DNA, where we've taken DNA from cells and we've put that DNA into a test tube, right? And then from that isolation, we did something called PCR. And PCR was the amplification. So we took one piece of DNA and we made it into millions and millions and millions and millions and millions of pieces of DNA. And that, again, is all in a test tube, right? So we took one person's DNA and we've amplified that. Okay, so let's say we had, I don't know, 10 to the 5th amount of DNA here. Here we have, 10 to the 20th, right? We've amplified it. Okay, what we want to do now is we want to compare, and we compare with gel electro. Okay, I'm not going to write the whole thing out. Gel electrophoresis. And what we're going to do here is we're going to compare DNAs, right? So one really good example of a usage for gel electrophoresis is at a crime scene, right? And I think that's what the lab is about, because it's talking about a crime scene. So at a crime scene, you have an individual that we call the victim, right? And the victim is the person that was maybe killed or murdered, right? And we'll call that victim Joe. Okay. And then at the crime scene, Joe's lying there, unfortunately passed away. And there is blood of Joe there, and there are cells of Joe there. Joe is there himself, but he's just not alive. But we can isolate his DNA. We can PCR his DNA, right? So we have a test tube of Joe's DNA that has been PCR'd. So we have lots and lots and lots of Joe DNA fragments, okay? And then at the crime scene, we find blood, okay, from what we call a suspect. Okay, and that suspect, we don't know who it is, but we found blood that's not Joe's, right? We found blood, we found tissue, we find hairs that are not belonging to Joe. So we're going to call that suspect person X, because we don't know who it is. But we were able to get that person's DNA. We were able to isolate it from the cells that we found at the crime scene, and we were able to PCR that DNA. So we have lots and lots and lots and lots of copies of suspect X's DNA, right? So now, if you're a crime scene investigator or if you're a police officer, okay, what you have to do is you have to go on the scene and you have to do some digging around through Joe's kind of personal life to find out who would, be a person that might want to hurt Joe, right? And maybe it's not a personal person, maybe it's a random thing, but that's part of the being a cop and being a police officer and a detective or whatever, right? And let's say you narrow it down to 3 people, suspect 1, suspect 2, and suspect 3. Okay. Now, you have three suspects here. Now, let's say there's not enough evidence to kind of make this person guilty, right? So there's no videotape that shows this person killing Joe. There's no witness that says this person killed Joe. So all you have to rely on is the DNA found at the crime scene, okay, of the suspect. And what we can do is we can go around to three individuals, right? Let's say this is a girlfriend of his, okay, an ex-girlfriend. Let's say this is a buddy of his, and let's say that this was a coworker of his, right? That you suspect for some reason. The girlfriend got mad at him. The buddy is in love with the girlfriend. The coworker got fired because of him or something. Who knows? There's motive behind these three people. And we suspect that this DNA belongs to one of these people's DNA. Now, it might not, right? It might not belong to any of these three people, but let's just assume it does, right? Let's assume it belongs to one of these three individuals. So what we can do is we can take the DNA found at the crime scene and we can compare it to the DNA of these people. Okay. How we do that? We have to go through these processes. We have to take DNA from the ex-girlfriend. We have to take DNA from the friend. We have to take DNA from the coworker. Okay. And you have to get warrants for that. A judge has to issue a warrant. And a crime scene investigator, a CSI investigator, has to go to these individuals' homes and take samples from a cheek, or take samples from their hair, or something, whatever they need to do to get the cells. And they need to isolate the cells in a test tube, and then they have to amplify them through PCR. And what you have is you'll have amplified DNA for all three individuals. And now what we can do is we can use gel electrophoresis to compare this DNA to these three. And hopefully we get a match. Okay, so let's talk about that. So how do we do that? So we take, suspect X. We don't know suspect X, right? And we take that person's DNA. This person's DNA is the same in every single one of this person's cells, right? So it doesn't matter where you got the DNA from this individual. All the DNA of this individual will be the same in every one of its cells, right? So if this person skin cells are left behind, or his blood cells are left behind, or brain cells, or kidney cells, or whatever, the DNA of this individual will always be the same. Same thing for suspect 1, suspect 2, and suspect 3. All their DNA will be the same for every one of their cells, right? They'll be different from one another, but they'll all be the same for each individual, right? So what we want to do is we want to take something called a restriction enzyme. A restriction enzyme is an enzyme that cuts DNA at specific locations. Locations. I'm not going to fit it. Okay, locations. So what does that mean? So I can buy a restriction enzyme that looks for a certain pattern of DNA as far as those letters go, and it'll cut every time it sees that pattern. So let's say I buy a enzyme that every time it sees the letter sequence GGAA. Remember ATGC, right? ATGC. These were the letters that make up DNA. A always bonds to T, G always bonds to C. Okay, hopefully you guys remember that. Okay. If we take one side of the DNA, we should see letters going across, right? We should see letters that say A, T, C, C, G, G, A, C, C, A, G, G, A, T, T, A, G, G, A, C. Okay? So if we saw something like this, let's say this is this person's DNA, right? And we add this restriction enzyme. And this restriction enzyme cuts, every time it sees GGAA, it's going to cut it in half between the G's and the A's. Okay? Every time that GGAA shows up in this person's DNA, it's going to cut it between. So let's see. GGAA. The restriction enzyme will cut. GGAA. It'll cut it again. GGAA. It'll cut it again. Okay? So that when I'm done cutting the DNA up, it's going to leave me with 1, 2, 3, 4 pieces of DNA. This piece of DNA is 1, 2, 3, 4, 5, 6 letters long. This one is 1, 2, 3, 4, 5, 6, 7, 8 letters long. This one is 1, 2, 3, 4, 5, 6, 7 letters long. And this one is 3 letters long. Okay? Every piece of DNA in this individual's body is exactly the same. So every time you add this enzyme to this person's DNA, it's going to cut it the same exact way because that person's DNA is the same in every cell that it has. Okay? So if I PCR'd this like I should have, and I have billions of copies of this, I should get billions of copies of this segment, and billions of copies of this cut segment, and billions of copies of this segment, and billions of copies of this segment, right? If I take another person's DNA, okay, another person's DNA might look like this. A, C, C, A, C, 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 T, T, G, A, G, G, A, C, C, T, A, C. Okay? This person's DNA is going to be cut differently because it only has one GGAA that gets cut. So when this person's DNA gets cut, you get 1, 2 pieces instead of 4 pieces like this person's DNA, right? And this one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is 13 letters long. That's a big piece, right? And then this one is 1, 2, 3, 4, 5, 6, 7, 8 letters long, right? But it only has 2 pieces compared to the 4 pieces, right? So that's what we're going to do. We're going to add the same enzyme, and that's really important, okay? Really, really, really important. We're going to add the same enzyme. Add the same restriction enzyme to all DNA samples. Okay? We want to make sure we add the same enzyme because we want them all to be cut with the same letter sequence, GGAA in this case. Okay, if we added different restriction enzymes that cut at different sequences, if I added GGAA to this one and I added GTTC to this one, okay, that's going to be a problem because they're not all being cut the same. We want them to be all cut the same. Okay, so we add all these enzymes, this enzyme to all of these different samples. So what we're going to have is we're going to have 4 test tubes, and each test tube is going to have DNA that's been cut differently. But what are we hoping? We're hoping that one of these 3 test tubes is cut the exact same way that this test tube is cut, right? Because we want one of these individuals to match this one so we can know who the killer was. Now, again, it doesn't have to be any of these 3 in real life, but in our scenario, one of these 3 is going to be the killer. So one of these 3 test tubes has to match that one 100% exactly. Okay? So let's take a look at how we do that. So after we cut the enzymes up, or after we cut the DNA up, right, here are my 4 test tubes. X, X1, X2, X3. After they're all cut up, what we're going to do is we're going to put them in what we call a gel. And a gel is like a 3x4 piece of jelly, just like Jell-O that you would eat for dessert. And the Jell-O has little holes in it that we call wells. And what we do is we take the sample of each and we put them in different wells. So we'll take all the different pieces of the suspect from the crime scene and we'll put it into one well. We'll take all the pieces of the first suspect and put it in the second well. All of this person's pieces and put it in the third well. All of this person's pieces, put it in the fourth well. And what we're going to do is we're going to use electricity. This is where the electro part of this word comes from. We're going to take electricity to cause the DNA to run down or through the gel. Okay, so DNA itself, DNA has a negative charge. Okay, so what we're going to do is we're going to hook up a negative electrode to the side where the DNA is, and we're going to hook up a positive electrode to the opposite end, because opposites attract. Opposites attract. And we're going to turn on the electricity. And what's going to happen is the DNA, because it's negatively charged, is going to be attracted to the positively charged other side. And that's going to happen for all of the DNA. So you might be saying, Professor, how is this going to help me find out who's alike and who's different? Well, the reason for that is larger pieces of DNA move slower than smaller pieces. Larger pieces of DNA move slower. So that first suspect had 4 pieces of DNA of varying lengths. Okay? The biggest piece is going to move slower than the smallest piece. Okay, so this is going to move slow because it's so big. It's like if I made you pull a car with a rope across a parking lot, and then I asked you to move a little wagon with a paint can in it across the same parking lot. Which one would you be able to move easier? You'd obviously be able to move the little wagon a lot faster than you'd be able to move the car if you were able to move the car at all, right? So what's going to happen in this gel is that in the first well, when you put all the pieces in here, you're putting all of these pieces into that well. And what's going to happen is the really small ones are going to move really quick down the gel towards the positive electrode. And the heavy pieces are going to stay at the top or towards the top. Okay. And what you're going to see is you're going to see things called bands. You're going to see banding. And the bands are going to be how far those pieces moved, right? So let's say, let me just erase this because it's a little messy. Actually, let me go on here because I think I can show you an actual gel. Okay, so here, take a look at this picture. Okay, if we take a look at this picture here, what we see is we see these lines, and these lines are called bands. Okay, and here is in this picture, this happens to be the what do you call it? The common one, the control group. Okay, and in this control group, they have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bands, and you can see how the bands get smaller and smaller as they go down to the base, because the smaller ones move faster than the bigger ones. And here's what we're doing is we're comparing sample A, sample B, and sample C together, right? We're comparing them to see which one is similar to one another. And that's just like what we're doing here. We want to compare, let me get a new thing here. We want to compare the individual to the suspects. So we're going to add the DNA of each one of these individuals, all the pieces, and we're going to run them. And all of them are going to have different sized pieces and different amounts of pieces. And that's what this picture is showing you, right? So here, sample A, so we can say that this was the ex-girlfriend for argument's sake. Her DNA was cut into 1, 2, 3, 4, 5 pieces when we added that enzyme. Okay, this person, 1, 2, 3, 4 pieces of DNA it was cut up into, because this person's DNA is different. So that enzyme is going to cut this person's DNA differently than this one's. And then sample C, 1, 2, 3, 4. The same number of B, right? B has 1, 2, 3, 4, but the sizes are different, right? This one is a little bit, actually, those might be the same, right? The first DNA piece between A, B, and C are all the same. But sample A has a piece of DNA of a certain size that B does not have and C does not have, because all the DNA is going to move at the same size, or the same size is going to move at the same rate, right? So this piece of DNA and this piece of DNA and this piece of DNA, they're all the same size. It doesn't matter that their letter sequences are different. It doesn't matter if it's AATTT and this one says AATTG and this one says ACCCCT. all because they're all in the same spot because they all have the same amount of letters. It doesn't matter what the letters are. Just because the letters are the same amounts, they're going to stop at that point. Same thing here. So let's say this is 15 letters long. These two pieces don't have 15 letter long sequences or pieces, and we know that because there's no band here. Okay, let's say this one has to be less than 50. If this is 15 and this one moved quicker than 15, and we know the slower ones are the heavier ones or the bigger ones, this one has to be less than 15, right? So let's say this one's 10, right? And that means that sample B has a piece that's 10, but sample A doesn't, and neither does sample C because they don't have bands there. This one has to be lower than that or smaller than that. So let's say this one is 8. Sample A has an 8-piece segment. B does not. C does not because there are no bands. Okay, this one is 6. A does not have one. B does not have one. C has one. Here, this one's 4, right? And this 4, sample A has a 4, and sample C has a 4, or something closer. Maybe that's 7, okay, because it looks like it's a little higher than that one. Okay, and that's what we do as scientists. As scientists, what you do is you compare the bands. How many bands line up, right? So none of these samples, A, B, or C, are exactly alike one another because none of them have the same pattern, right? So this pattern differs from this pattern and differs from this pattern. So none of these patterns match. What we want is we want a matching pattern, right? So let's say that the pattern for our suspect, the suspect that we found at the crime scene, let's say this is the pattern. We want to see a pattern that is exactly the same. So here's the ex-girlfriend. That pattern is not the same as this pattern. So the ex-girlfriend is out. Okay. Let's say here is the best friend. Okay, now that you got scared. You thought the best friend was the culprit here, right? Because 1, 2, 3 patterns match, but this last one does not. Okay, this last one does not match this, right? This person has a piece that's way heavier than this piece. Okay, and then so that means that person's out. So then all we have left is the coworker. Okay, the coworker that Joe got fired for some reason. Okay, and lo and behold, that's our culprit. Okay, so the person who has the matches, this one matches with this one, 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 100% match. This is our person who is the person at the crime scene. Now that doesn't mean that that's a murderer, right? All that means is that this person's DNA was found at the crime scene. The police still have to prove that this person murdered Joe. Okay. So with that, okay, I didn't give you all the information, but a lot of the information is there. What I want you to do is go to this website, go through the problem, go through the explore, go through the procedure. Okay. Do everything it asks you to do. Make sure you click on each one of these. Okay, because all this stuff is going to be on the test. You're responsible for getting all of the definitions of all of these things here. Okay. And do all the questions in the lab notebook. Okay. Do the prediction question, the data, and the 6 analyze conclusion questions. You're going to do all of that, not on here. Okay. You're not going to do them in here. You're going to actually transfer all this information, okay, to a Google document, and you're going to upload that Google document to this assignment. If you have any questions, please feel free to ask me. Okay, everybody? All right. Thank you very much. Have a good night.